Hello, and welcome to the Sleepy Science Facts channel. Tonight, we'll gently drift into the unknown, into the quiet questions that science has not yet answered. Despite everything humanity has discovered, the universe remains filled with riddles, paradoxes, and silent mysteries that no one can fully explain. Some of them are cosmic, stretching across vast galaxies and swallowing light inside black holes. Others exist much closer to home, hidden within Earth's oceans, drifting through the atmosphere, or unfolding inside our own bodies. These unanswered questions remind us that science is not a finished book of final truths. It is an ongoing story, still being written. Every mystery opens a doorway to wonder, a gentle reminder that we are explorers living inside a universe far larger than we can truly comprehend. If you enjoy drifting to sleep while listening to scientific wonders, feel free to like, subscribe, or share your thoughts in the comments. It helps others find their way here as well. But for now, allow these questions to carry you. And when you're ready, let us begin. We still do not know why the universe exists at all. It may seem like the simplest question imaginable. Why is there something rather than nothing? And yet, science offers no clear answer. Physics can describe how the universe behaves once it exists. Cosmology can trace its history back to the Big Bang. But why there is a universe in the first place? Why there are laws that allow it to exist at all? Remains unresolved. Quantum physics suggests that what we call nothing is not truly empty. Even the vacuum of space teems with activity, as fleeting particles briefly appear before vanishing again. Some physicists propose that the universe itself may have emerged in a similar way, that absolute nothingness is unstable, and something must inevitably arise. Others suggest that our universe may be just one of countless universes within a vast multiverse, each coming into existence with its own unique laws. But even this idea leads to a deeper mystery. Why should the multiverse itself exist at all? Philosophers sometimes argue that existence is the natural state, that true non-existence may be impossible. Perhaps reality, in some form, must always be. But these ideas remain beyond our ability to test. No telescope, no particle accelerator can measure why being exists instead of nothingness. Every other question in science rests upon this one. Every star in the sky, every atom in your body, every law of nature exists atop a foundation we cannot explain. The simple fact that reality exists at all remains the deepest mystery we face. The spark that set the cosmos in motion is still unknown. We can trace the universe's story back nearly 14 billion years to a time when everything was compressed into a hot, dense state. We call this beginning the Big Bang. But what caused it? That question remains unanswered. Cosmologists have reconstructed a detailed history of the universe from the moment it was fractions of a second old. During that earliest instant, space itself may have expanded at an extraordinary rate in a process known as inflation. This rapid expansion smoothed the universe and shaped its structure. Yet we still do not know what triggered inflation. Why did it begin? And why did it end? Some theories imagine the Big Bang as a quantum fluctuation, a tremble in the fabric of reality that gave rise to space and time themselves. Others suggest the Big Bang was not the first event at all, but merely one chapter in an endless cycle of universes being born, collapsing, and beginning again. The mystery deepens when we consider time itself. If time was born with the universe, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the James Webb Space Telescope, offer stunning images of the early universe, but none of them can peer into the very first instant. We know the universe began. We can measure its age, chart its expansion, and study the faint afterglow it left behind. But the true first cause, the spark that ignited everything, remains hidden in darkness. Time always seems to move forward, yet no one truly knows why. Each moment slips from the present into the past. We remember yesterday, but never tomorrow. A shattered glass never reassembles itself. Heat flows from hot coffee into the air, but never the other way around. In our experience, time has only one direction. This is known as the arrow of time. What makes this so strange is that the fundamental laws of physics do not demand it. At the smallest scales, particles can move forward or backward in time with equal consistency. The equations remain symmetrical. Nothing in them requires time to flow only one way. And yet, our entire world depends on this irreversible march. Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in an extraordinarily ordered state and has been slowly unwinding ever since. But why did it begin that way? Why did the cosmos start with such low entropy that time could even have a direction at all? Some physicists believe the arrow of time emerges from the way information spreads. Others suggest it is tied to the expansion of the universe itself. But none of these explanations are complete. Time is something we inhabit every second of our lives, and yet why it flows forward and only forward remains one of the most haunting mysteries in science. Most of the universe is made of something we cannot see. When astronomers measure how galaxies rotate, they discover something deeply puzzling. Stars near the outer edges of galaxies move far faster than they should. According to everything we know, they ought to fly apart and drift into space. Yet they don't. Instead, galaxies remain held together by an invisible grip. The only explanation is that most of the mass in the universe is hidden from view. We call this unseen substance dark matter. Dark matter does not emit light. It does not absorb light. Our telescopes cannot see it directly, and yet its presence is unmistakable. Its gravity shapes galaxies, bends the paths of light traveling across the cosmos, and leaves subtle fingerprints in the large-scale structure of the universe. So what is it? Scientists have searched for decades. Some believe dark matter is made of undiscovered particles, such as weakly interacting massive particles, or WIMPs. Others suggest axions, ghostly particles that barely interact with ordinary matter at all. There are even theories proposing that dark matter could consist of black holes formed shortly after the Big Bang. Despite enormous effort, no explanation has been confirmed. Experiments buried deep underground wait patiently for a single dark matter particle to collide with an atom. So far, none have. For now, this hidden mass, 5 times more abundant than ordinary matter, remains one of the greatest unsolved mysteries of the universe. Another invisible force is stretching space itself faster and faster. In the late 1990s, astronomers studying distant supernovae expected to see the universe's expansion slowing down. Gravity, after all, should be pulling everything back together. Instead, they found the opposite. The universe is not just expanding, its expansion is accelerating. This discovery means that some unknown energy is embedded in space itself, pushing galaxies apart at ever-increasing speeds. We call it dark energy, though the name is merely a label for our ignorance. Dark energy makes up nearly 70% of the entire universe, yet we have no idea what it truly is. One possibility is that it is a property of empty space itself, a constant energy woven into the vacuum. Another idea suggests it points toward new physics, perhaps a dynamic field that evolves over time. Some theories even hint that our understanding of gravity may be incomplete. What makes this mystery especially unsettling is its consequence. The ultimate fate of the universe depends on dark energy. If it remains constant, galaxies will drift farther apart until the cosmos grows cold and empty. If it grows stronger, it could eventually tear apart galaxies, stars, planets, and even atoms themselves. We can measure its effects, but its true nature remains hidden. Dark energy is the unseen hand shaping the future of everything. The laws of physics themselves appear strangely tuned for life. The universe seems balanced on a knife's edge. If gravity were slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form at all. If the electromagnetic force were altered by even a tiny fraction, atoms could not bind together. The smallest changes in the constants of nature would erase the possibility of life entirely. This puzzle is known as the fine-tuning problem. Why do the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or the nuclear forces to possess their particular strengths. And yet, if they were even slightly different, the universe would be lifeless. Some scientists argue this is coincidence. Others suggest a multiverse exists, containing countless universes with different laws, and we simply inhabit the rare one where life is possible, a cosmic lottery win. Another idea proposes that a deeper principle, still undiscovered, forces the laws of physics to take these exact values. For now, no explanation has been proven. But when we look around at stars, planets, and the simple fact that we are able to ask this question, the universe feels improbably, almost uncannily suited for life. And why that is remains one of science's greatest mysteries. No one knows whether the universe goes on forever or ends somewhere. The observable universe spans roughly 90 billion light-years across, but beyond that, we cannot see. Light has only had so much time to travel since the Big Bang, creating a cosmic horizon beyond which we are blind. What lies beyond that edge? One possibility is that the universe is infinite, stretching endlessly in all directions with no boundary at all. If so, it may contain an unending number of galaxies, stars, and perhaps even worlds like our own. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. In such a cosmos, traveling far enough in one direction could eventually bring you back to your starting point. Scientists search for clues in the cosmic microwave background, the faint afterglow of the Big Bang. Its subtle patterns may reveal the universe's shape. So far, the evidence suggests the universe is nearly flat. But flatness alone does not tell us whether it is infinite. For now, the true size and shape of the universe remain hidden just beyond our reach. Beyond the horizon of what we can see, there may be vast regions of the universe forever hidden from us. When we look into space, we are also looking back in time. The most distant galaxies we can observe are sending us light that has traveled for more than 13 billion years. But beyond a certain distance lies a realm we will never witness directly, the unobservable universe. This cosmic boundary is not a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues to exist, but no signal from there can ever reach us. What might lie beyond? Perhaps it is much the same. Galaxies, stars, and planets stretching endlessly beyond our sight. Or perhaps it is profoundly different, with regions governed by unfamiliar conditions, or even entirely different physical laws. Some theories of cosmic inflation suggest that our observable universe is just one bubble within a much larger reality. If this is true, then the portion of the universe we can see is only a tiny island surrounded by an ocean of unknown space. The sky above us may represent only a fraction of what truly exists. The rest of the universe remains silent and unreachable, a permanent unknown. Some scientists believe there may be other universes beyond our own. The idea of a multiverse is among the boldest in modern science. It proposes that our universe is not unique, but one of countless others. Each universe could have its own laws of physics, its own history, and even its own number of dimensions. This idea arises naturally in some theories. Inflation may generate bubble universes, each breaking away with its own properties. String theory predicts a vast landscape of possible realities, each defined by different physical rules. In this view, our universe is simply one outcome among many. This could even explain fine-tuning. We live in a universe suited for life because only in such universes can observers exist. But there is a problem. If other universes lie beyond our cosmic horizon, we may never be able to observe them. No light, no signal, no information could ever cross the boundary. This makes the multiverse both fascinating and controversial. It stretches the definition of science itself, because ideas that cannot be tested may never move beyond speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, remains one of the most intriguing mysteries in physics. Space and time themselves may be woven from deeper rules we have not yet uncovered. Einstein's theory of general relativity revealed that space and time are not rigid backdrops. They are flexible and dynamic, capable of bending and stretching. Gravity is not a force in the usual sense, but the curvature of space-time itself. Planets follow curved paths. Light bends near massive objects. Time slows in strong gravitational fields. But at the smallest scales, relativity collides with quantum mechanics. In relativity, space-time appears smooth and continuous. In quantum theory, everything else is grainy, fluctuating, and uncertain. Reconciling these two pictures is one of the greatest challenges in science. Some theories suggest that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps networks of quantum information or patterns of entanglement that give rise to geometry itself. In this view, space-time is like a surface, and beneath it lies a more basic reality we cannot yet perceive. Others question whether time itself is real, proposing that it may be an illusion produced by deeper processes. If this is true, then our most basic intuition about reality would be mistaken. Space and time feel like the stage on which the universe unfolds. Yet the stage itself may not be what it seems. What space and time truly are remains one of the most profound unanswered questions in science. A single particle can exist in two places at once, and we still do not know how this is possible. Quantum mechanics tells us that particles do not have definite positions until they are measured. Instead, they exist in a state called superposition, a spread of probabilities where many outcomes coexist at the same time. An electron can be here and there simultaneously. In famous experiments, a single particle passes through two slits at once, interfering with itself like a wave. Only when we observe it does the particle seem to choose a position. This is not just theory. Experiments have repeatedly confirmed superposition, not only for electrons, but for molecules thousands of times larger. Physicists have even created fragile quantum states where small objects exist in overlapping possibilities. And yet, no one truly understands what this means. Does the particle physically exist in multiple places at once? Or is superposition merely a reflection of our incomplete knowledge? Some interpretations suggest reality splits into multiple branches. In one branch, the particle appears here. In another, it appears there. Other interpretations propose that reality itself is undefined until measurement occurs. Whatever the truth may be, the ability of a single particle to seemingly occupy multiple states at once remains one of the strangest and most unsettling mysteries of modern science. Entangled particles appear to echo one another across vast distances. When two particles become entangled, their properties become linked in a way that defies common sense. Measure one particle, and you instantly know the state of the other, even if they are separated by light years. Albert Einstein famously referred to this as spooky action at a distance, because it seemed to violate the cosmic speed limit. Nothing, according to relativity, should travel faster than light, and yet experiments have shown entanglement is real. Photons, electrons, and even small collections of atoms have been entangled and separated by kilometers. No signal appears to travel between them, but the correlations remain perfect. It is as if nature keeps a hidden ledger, ensuring the outcomes remain synchronized. What does this mean? Some physicists believe entanglement implies that reality is fundamentally non-local, that the universe is connected more deeply than space and time allow us to imagine. Others argue it points toward hidden variables we have not yet discovered. Still others suggest that information itself may be the true foundation of reality. We already use entanglement in quantum computing and secure communication, yet we cannot fully explain why it works. The universe whispers across distances, and we still do not know how. Observation itself seems to change reality, and no one knows why. One of the most unsettling discoveries in physics is that the act of measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when no one observes them, creating interference patterns. But when we measure which slit a particle passes through, the wave-like behavior disappears. The outcome changes simply because it was observed. Why should this be? One explanation suggests that the wave function, the mathematical description of all possible states, collapses into a single outcome when observed. But what counts as an observer? Is it a measuring device? A conscious mind? Or is collapse merely an illusion masking deeper laws we have yet to uncover? Some interpretations propose that all possible outcomes occur, branching into multiple realities. Others argue that particles only appear definite when information about them becomes irreversible. None of these ideas have been conclusively proven. What we do know is that the boundary between observer and observed is not as clear as we once believed. The universe appears to behave differently when it is watched, and no one knows why. Gravity is far weaker than every other force, and we do not know why. Gravity shapes the cosmos. It holds planets in orbit, binds galaxies together, and governs the motion of stars. Yet compared to the other fundamental forces, gravity is astonishingly weak. A small magnet can overcome the gravitational pull of the entire Earth. Why should this be? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate with tremendous strength on tiny scales. Gravity, by comparison, is feeble. Physicists have wrestled with this hierarchy problem for decades. One possibility is that gravity spreads into hidden dimensions beyond the ones we can see, diluting its strength. Another idea suggests gravity is fundamentally strong, but masked by unknown physics at small distances. Despite centuries of study, we still do not understand why gravity is so much weaker than the other forces. This imbalance is not a trivial curiosity. It is essential to the structure of the universe. Without weak gravity, stars and galaxies could not exist. The weakness of gravity is the quiet mystery that makes the cosmos possible. Einstein's description of the universe and the quantum world both work, yet they refuse to fit together. General relativity describes the large-scale structure of the universe with extraordinary accuracy. It explains the motion of planets, the bending of light, and the behavior of galaxies. Quantum mechanics, meanwhile, governs the microscopic world of particles with astonishing precision. Both theories have been tested again and again, and both succeed every time within their own domains. But they do not agree with each other. When scientists try to describe situations where gravity and quantum effects must work together, such as inside black holes or during the first moments after the Big Bang, the equations collapse into infinities. Numbers spiral out of control. The mathematics breaks. The two frameworks are fundamentally incompatible. For decades, physicists have searched for a theory of everything, a single framework that unites relativity and quantum mechanics. Candidates like string theory and loop quantum gravity offer elegant ideas, but none have been confirmed by experiment. Without a unifying theory, we cannot fully understand the birth of the universe or the nature of space-time at its smallest scales. The fact that our two most successful theories describe different realities is one of the greatest paradoxes in science. Both are correct, yet together they fail. The true heart of a black hole remains unknowable. Black holes are regions where gravity becomes so intense that nothing, not even light, can escape. As matter falls inward, it is crushed and compressed beyond imagination. According to Einstein's equations, everything collapses into a single point of infinite density, known as a singularity. But infinity is often a sign that our theories have reached their limit. What truly exists at the center of a black hole? Some physicists believe singularities are real, places where the known laws of physics simply break down. Others suspect that a deeper theory, perhaps a quantum theory of gravity, replaces the singularity with something else entirely. A finite core, a loop of space-time, or a structure we do not yet have the language to describe. The event horizon hides the interior of a black hole completely. No information from within can ever reach us. For now, the heart of a black hole is sealed away beyond observation and beyond certainty. It remains one of the most inaccessible mysteries in all of science. We still do not understand what singularities truly are. A singularity is a place where our equations predict infinite density, infinite curvature, and the collapse of space and time themselves. Black holes contain them. The Big Bang may have begun with one. But are singularities real features of nature, or do they simply mark the breakdown of our theories? Many physicists believe singularities signal the limits of general relativity. Somewhere beyond them, a new theory must take over, one that unites relativity with quantum mechanics. In such a theory, infinities may dissolve into something finite and understandable. Until then, singularities remain puzzles at the edge of physics. They are boundaries where our knowledge ends and our models fail. What lies beyond them is hidden, waiting for a deeper understanding of reality. Whether information is lost inside a black hole remains an open question. When matter falls into a black hole, it seems to vanish forever. But in physics, information, the detailed description of a system, is supposed to be preserved. So what happens to the information carried by matter that falls into a black hole? Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon cause them to emit faint radiation, slowly losing mass over immense spans of time. If a black hole eventually evaporates completely, what happens to the information it once contained? If information is destroyed, the laws of quantum mechanics are violated. If it escapes, then somehow it must be encoded in the Hawking radiation, a process no one fully understands. This puzzle is known as the black hole information paradox. Some scientists believe information is stored on the event horizon itself. Others propose that black holes connect to other regions of space-time, allowing information to escape in unexpected ways. Still others argue that our understanding of quantum mechanics itself may need revision. The fate of information inside a black hole is one of the most important unanswered questions in physics. It touches the deepest foundations of reality. Hawking radiation is predicted, but no one has ever observed it. In the 1970s, Stephen Hawking made a startling prediction. Black holes should emit radiation due to quantum effects near their event horizons. Over unimaginable timescales, they would slowly shrink and evaporate. This radiation, now called Hawking radiation, links quantum mechanics, gravity, and thermodynamics in a single idea. Yet, despite its importance, it has never been directly observed. Real black holes are surrounded by hot, turbulent environments that overwhelm the faint signal of Hawking radiation. Detecting it may be beyond our current technology. Laboratory experiments have created analogs using sound waves and fluids, offering indirect hints. But the real phenomenon remains unconfirmed. If Hawking radiation exists, it will reshape our understanding of black holes and space-time itself. If it does not, something even stranger must be happening at the edge of physics. Black holes may be more than cosmic dead ends. Some theories suggest they could be gateways to regions we have never seen. Black holes push physics to its limits. Inside them, space and time are twisted into forms we cannot fully describe. Certain solutions to Einstein's equations allow for the possibility that black holes could connect distant regions of space-time through tunnels known as wormholes. In theory, entering a black hole might lead somewhere else entirely. But this remains speculation. Wormholes, if they exist, may be violently unstable. The crushing gravity inside a black hole could destroy anything that attempts to pass through. And yet, the mathematics does not rule the idea out completely. Some physicists propose that the singularity at a black hole's center could mark the birth of a new universe, with its own space and time unfolding beyond our reach. Others suggest black holes may recycle information, seeding new cosmic regions. For now, these ideas remain untestable. No signal can escape a black hole's interior. Its secrets remain hidden behind the event horizon. Still, the notion that black holes could be more than cosmic graves, that they might be doorways to something beyond, remains one of the most tantalizing mysteries in physics. We still cannot fully explain how the first stars were born. In the early universe, darkness reigned. There were no galaxies, no planets, no heavy elements. Only vast clouds of hydrogen and helium drifted through expanding space. At some point, these clouds collapsed under gravity, igniting the first stars and ending the cosmic dark ages. But exactly how this happened is still unclear. These first stars, known as population 3 stars, were likely enormous, hundreds of times more massive than our Sun. They burned fiercely and briefly, living only a few million years before exploding as powerful supernovae. In their deaths, they forged the first heavy elements, seeding the universe with the materials needed for planets, chemistry, and eventually life. The mystery is that we have never directly observed a single one. Population 3 stars lived fast and died young, so long ago that their light has faded beyond easy detection. Astronomers search for indirect clues in the chemical fingerprints of ancient stars, hoping to find traces of their explosive births. The James Webb Space Telescope may one day glimpse their light, but for now, the exact process that sparked the first stars remains one of astronomy's great unanswered questions. Some galaxies formed supermassive black holes far too quickly. At the center of nearly every large galaxy lies a supermassive black hole, containing millions or even billions of times the mass of our Sun. We understand how black holes grow by consuming gas, stars, and other black holes. But in the early universe, astronomers observe supermassive black holes that formed astonishingly fast. Some already existed less than 1 billion years after the Big Bang. According to our models, there simply was not enough time for them to grow so large through ordinary processes. This raises difficult questions. Did these giants form from the direct collapse of enormous primordial clouds, skipping smaller stages entirely? Did the first generation of massive stars collapse into unusually large black holes that grew rapidly? Or is there an unknown mechanism that allowed them to feed at extraordinary rates? These ancient black holes challenge our understanding of galaxy formation. Solving this puzzle could reveal how galaxies themselves came into existence. For now, these early giants remain cosmic enigmas, objects that seem to have appeared before the universe was ready for them. No one knows why so many galaxies form elegant spiral shapes. When we picture galaxies, we often imagine graceful spirals, sweeping arms of stars curving outward like cosmic pinwheels. Our own Milky Way is one of them. But why do galaxies form such intricate patterns? One idea suggests spiral arms are density waves, similar to traffic jams on a highway. Stars move through these regions, briefly bunching together and creating the appearance of permanent arms. Another theory proposes that spiral structures arise from gravitational interactions as galaxies tug on one another and stir stars into curved patterns. Computer simulations can reproduce spiral shapes, but not consistently or completely. Spiral galaxies are common throughout the universe, yet their exact origin and long-term stability remain unsettled. Why some galaxies become elegant spirals while others evolve into featureless elliptical shapes is still an open question in astrophysics. When we look up and see the Milky Way stretching across the night sky, we are gazing from within one of these mysteries. Fast radio bursts flash across the universe, and their origins remain unknown. In 2007, astronomers detected a powerful radio signal that lasted only a few milliseconds. Since then, hundreds more have been discovered scattered across the sky. These mysterious signals are known as fast radio bursts, or FRBs. Each burst releases as much energy in a fraction of a second as the sun does in an entire year. What creates them? Some FRBs repeat, suggesting they come from ongoing processes. One leading explanation involves magnetars, highly magnetic neutron stars capable of releasing enormous bursts of energy. Other bursts appear only once, hinting at catastrophic events such as the collapse of massive stars or the merger of compact objects. Yet no single explanation accounts for all observed cases. FRBs travel across billions of light years, distorted by the matter they pass through. In the future, they may help astronomers map the distribution of matter across the universe. For now, they remain cosmic puzzles, brief, powerful shouts across the void whose source we do not yet understand. Pulsars shine with astonishing precision that still puzzles scientists. Pulsars are rapidly spinning neutron stars, the collapsed cores of massive stars that exploded as supernovae. As they rotate, beams of radiation sweep across space like the beams of cosmic lighthouses. When one of these beams crosses Earth, we detect a pulse. Some pulsars pulse hundreds of times per second with remarkable regularity. When they were first discovered in 1967, their precision was so uncanny that scientists briefly wondered whether they might be signals from intelligent civilizations. We now know they are natural objects, but their stability remains astonishing. Some pulsars keep time more accurately than our best atomic clocks. How can an object so extreme, a star compressed into a sphere the size of a city, maintain such perfect rhythm? The answer lies in their incredible density and powerful magnetic fields, but the details are not fully understood. Pulsars also glitch. Occasionally, they suddenly speed up or slow down in ways scientists cannot yet predict. These glitches may arise from interactions within their superfluid interiors, where physics behaves unlike anything we can reproduce on Earth. Pulsars are natural laboratories for extreme physics, yet they still keep secrets. Magnetars erupt with terrifying bursts of energy we do not fully understand. A magnetar is a rare type of neutron star with a magnetic field thousands of times stronger than that of ordinary neutron stars, and trillions of times stronger than Earth's. These immense magnetic fields twist and strain the star's crust. When the stress becomes too great, it snaps, releasing enormous amounts of energy in sudden bursts. Magnetars can unleash more energy in a single second than the sun produces in hundreds of thousands of years. We detect these eruptions as intense flashes of X-rays and gamma rays. But what precisely triggers them remains uncertain. Are these bursts caused by starquakes, shifts in the solid crust of the neutron star? Or are they driven by sudden rearrangements of the magnetic field itself, releasing energy like a snapping cosmic rubber band? Some fast radio bursts have even been linked to magnetars, suggesting they may explain at least part of the FRB mystery. Still, the full picture remains incomplete. Magnetars are rare, with only a few dozen known, yet their power is staggering, reminding us that the universe contains engines of energy we still struggle to comprehend. Cosmic rays strike Earth with unimaginable force, and we do not know where they come from. Every second, high-energy particles known as cosmic rays rain down on Earth from space. Most are protons traveling near the speed of light. Many originate from the sun or from exploding stars. But some cosmic rays are far more energetic than anything we can explain. The most extreme examples carry the energy of a fast-pitched baseball packed into a single atomic particle. No known natural process should be able to accelerate particles to such extraordinary speeds. These ultra-high-energy cosmic rays may come from supermassive black holes, active galaxies, or from exotic phenomena we have yet to understand. When they strike Earth's atmosphere, they produce cascades of secondary particles that spread across vast areas. Observatories like the Pierre Auger Observatory in Argentina track these showers, attempting to trace the particles back to their sources. But magnetic fields throughout space bend their paths, erasing the clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. Reminders that somewhere in the universe, nature operates particle accelerators far beyond anything humans have ever built. Vast cosmic voids stretch across the universe, and their origins remain uncertain. The universe is not evenly filled with matter. Instead, galaxies form a vast cosmic web, long filaments and dense clusters separated by enormous empty regions known as cosmic voids. Some of these voids span hundreds of millions of light years and contain very few galaxies at all. Why do they exist? Simulations suggest that gravity naturally pulls matter into filaments, leaving empty spaces behind. But the largest voids appear bigger and emptier than our models predict. Do they hint at new physics? Could dark energy influence how these vast empty regions grow? Or are they simply rare statistical extremes? Cosmic voids affect how light travels across the universe and may even provide clues about the nature of dark energy itself. For now, their true origins remain unclear. Staring into a cosmic void is like gazing into nothingness on the largest possible scale. Vast, silent regions with no clear explanation. How the universe will end remains unknown. The universe had a beginning, but will it have an end? Scientists consider several possible futures, each shaped by the behavior of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever. Stars burn out, galaxies fade, and the cosmos cools toward a state of near-total darkness. This is known as heat death. In another possibility, expansion eventually slows and reverses, pulling everything back together in a big crunch. A third outcome is even more dramatic: the Big Rip. In this scenario, dark energy grows stronger over time, tearing apart galaxies, stars, planets, and eventually even atoms themselves. Which fate awaits the universe? At present, observations suggest expansion will continue, but dark energy remains poorly understood, leaving the ultimate future uncertain. The universe may persist for trillions of years, or meet a far more violent end. For now, the destiny of everything that exists remains one of science's greatest unanswered questions. Something triggered cosmic inflation, but no one knows what. In the first tiny fraction of a second after the Big Bang, the universe is thought to have expanded at an extraordinary rate in a process called inflation. This idea helps explain why the universe appears smooth and uniform, and why tiny fluctuations grew into galaxies and clusters. But what caused inflation? Some theories propose a mysterious energy field that briefly dominated the universe before fading away. Others suggest inflation is tied to the quantum structure of space-time itself. We see possible fingerprints of inflation in the cosmic microwave background, where subtle patterns match theoretical predictions. Yet inflation remains debated. Something caused the universe to grow unimaginably fast, shaping everything that followed. But the spark behind inflation remains hidden, a missing chapter in the story of creation. The origin of life on Earth remains unknown. Life appeared on Earth more than 3.5 billion years ago, but how it began is still a mystery. Fossils show that simple organisms existed surprisingly soon after the planet cooled. But how did non-living chemistry cross the boundary into biology? One idea suggests life began with self-replicating molecules, such as RNA, capable of storing information before DNA existed. Another proposes that life emerged near hydrothermal vents on the ocean floor, where heat, minerals, and chemistry combined. Some scientists even suggest life's building blocks arrived from space, carried by comets and meteorites during the early bombardment of Earth. Each idea has evidence. None are proven. Researchers have created amino acids and other basic molecules in laboratory conditions meant to mimic early Earth. But creating a fully living system remains beyond our reach. The origin of life may have been a rare event, or a natural outcome whenever conditions are right. Until we find clearer evidence, the moment when chemistry awakened into biology remains one of science's deepest mysteries. We still do not know whether life began in the oceans or on land. Earth offered many possible cradles for life. The oceans seem like an obvious birthplace. Hydrothermal vents provide steady energy and rich chemistry, and many scientists believe life may have emerged within mineral compartments deep beneath the sea. But another possibility lies on land. Some researchers argue that shallow pools, repeatedly drying and refilling, could have concentrated molecules and driven the reactions needed to build life's components. Ultraviolet light from the sun may have powered crucial steps in this process. Both environments have strengths and weaknesses. The ocean dilutes molecules, making interactions difficult. Land-based pools may have been unstable and short-lived. Until stronger evidence emerges, we do not know whether life first stirred in the deep oceans or in sunlit waters on land. The answer lies buried in ancient rocks that have long since been transformed. Life may not be as rare in the universe as we once thought, or it may be exceedingly uncommon. For decades, scientists have searched the cosmos for signs of life beyond Earth. We now know that planets are abundant. Nearly every star appears to host worlds of its own. Some of these planets orbit within their star's habitable zone, where temperatures allow liquid water to exist. Others possess thick atmospheres, subsurface oceans, or chemical energy sources that could support life. And yet, despite this abundance, we have found no clear evidence of living worlds beyond our own. This contradiction is known as the Fermi paradox. If life is common, where is everyone? One possibility is that life rarely progresses beyond simple forms. Another suggests that intelligent civilizations tend to destroy themselves before spreading far into the galaxy. Some may choose not to broadcast their presence at all. There is also the possibility that we are early, among the first intelligent species to emerge, or that advanced civilizations exist, but in forms we cannot yet recognize. The silence of the universe may be temporary, or it may be telling us something profound about the rarity of intelligence. The paradox remains unresolved. We do not know how consciousness arises from matter. Consciousness is the most intimate mystery we face. It is the experience of being, of thoughts, feelings, awareness, and selfhood. Neuroscience has mapped many regions of the brain and linked them to specific functions. We can observe neurons firing and signals traveling through neural networks. But how do these physical processes produce subjective experience? Why does matter arranged in a particular way give rise to sensations, emotions, and thoughts? Some scientists believe consciousness emerges from complexity, that when systems reach a certain level of organization, awareness appears naturally. Others argue that consciousness may be a fundamental property of the universe, woven into reality itself. There are even theories suggesting that consciousness plays a role in shaping the physical world. Despite decades of research, there is no agreed-upon explanation. The so-called hard problem of consciousness remains unsolved. It is the gap between objective processes and subjective experience, a gap science has not yet bridged. Sleep itself remains deeply mysterious. Every night, humans surrender consciousness for hours at a time. During sleep, our brains remain active, yet our awareness fades. Why do we sleep? Sleep is essential. Without it, cognition deteriorates, emotions destabilize, and the body begins to fail. Yet its ultimate purpose remains unclear. Some theories suggest sleep allows the brain to consolidate memories, clearing out unnecessary information. Others propose it helps repair cells, regulate metabolism, or balance neural connections. Dreaming adds another layer of mystery. Dreams can feel vivid, emotional, and meaningful, or completely nonsensical. Why the sleeping brain generates these internal worlds remains uncertain. We spend nearly a third of our lives asleep, moving in and out of consciousness every day. And yet, why sleep evolved and what it truly does remains an open question. Dreams may not be random at all. For a long time, dreams were considered meaningless byproducts of neural activity. But modern research suggests they may serve important functions. Some scientists believe dreams help us process emotions, rehearse social situations, or integrate memories. Others argue they allow the brain to explore possibilities in a safe, simulated environment. But none of these explanations fully account for the richness and variety of dreams. Why do some dreams feel intensely real, while others vanish instantly upon waking? Why do certain images and themes repeat across cultures and individuals? Neuroscience can describe what parts of the brain are active during dreaming, but it cannot yet explain why dreams feel the way they do. Dreams remain a private universe within each mind, fleeting, powerful, and largely unexplained. Memory itself is fragile and unreliable. We trust our memories, but they are far from perfect. Every time we recall an event, the memory changes slightly. Details are altered, emotions shift, and false elements can be introduced without our awareness. The brain does not store memories like a video recording. Instead, it reconstructs them, piecing together fragments of information each time. This makes memory both flexible and fallible. Why did evolution favor such an unreliable system? Some researchers suggest that flexible memory allows us to imagine the future, adapt to new situations, and learn from patterns rather than exact details. Still, the mechanisms by which memories are stored, altered, and retrieved remain only partially understood. Our personal histories are shaped by a system that constantly rewrites itself, a quiet mystery within every mind. Human intuition often fails when faced with true randomness. We like to believe that events follow patterns. When something unusual happens, we search for meaning, intention, or hidden causes. But the universe does not always cooperate. At the quantum level, randomness appears to be fundamental. Certain events, such as the exact moment a radioactive atom decays, cannot be predicted, even in principle. They are not the result of hidden variables we have failed to detect. They appear to be truly random. This challenges our deepest assumptions about causality. If events can happen without cause, what does that mean for the structure of reality? Some physicists argue that randomness is only apparent, masking deeper laws we have not yet uncovered. Others accept that uncertainty is woven into the fabric of existence. Probability governs everything from quantum particles to genetic mutations and evolutionary change. The universe may not be a perfectly ordered machine, but a system where chance plays a fundamental role. Why randomness exists at all, and whether it is truly irreducible, remains an open question. Mathematics describes reality with uncanny precision, and no one knows why. Abstract equations, created in the human mind, often turn out to describe the physical universe with extraordinary accuracy. Complex numbers, invented for mathematical convenience, later became essential to quantum mechanics. Non-Euclidean geometry, once a curiosity, became the foundation of general relativity. This strange effectiveness of mathematics has puzzled scientists and philosophers alike. Why should the universe obey mathematical laws at all? And why should human-created mathematics map onto reality so perfectly? Some believe mathematics is discovered, an intrinsic structure of the universe that we gradually uncover. Others argue it is invented, a language we impose on nature. Neither explanation is fully satisfying. The deep connection between mathematics and reality remains one of the most profound mysteries in science. The laws of physics may not be constant forever. We assume that the fundamental constants of nature are fixed, that gravity, electromagnetism, and other forces behave the same everywhere and always. But what if this is not true? Some observations suggest that certain constants may have changed slightly over cosmic time. Other theories predict that physical laws could vary in different regions of the universe. If true, this would radically alter our understanding of reality. It would mean that the universe has not only a history, but evolving rules. So far, evidence remains inconclusive. Measurements are difficult, and alternative explanations exist. Still, the possibility that the laws of physics themselves are not permanent adds another layer of mystery to the cosmos. We do not know why matter dominates over antimatter. According to physics, the Big Bang should have produced matter and antimatter in equal amounts. When they meet, they annihilate each other, leaving only energy behind. If that were the whole story, the universe should contain nothing but radiation. And yet, here we are. Somehow, a small excess of matter survived. This imbalance, known as baryon asymmetry, allowed galaxies, stars, planets, and life to form. Physicists have identified processes that can produce slight asymmetries, but none are sufficient to explain the amount of matter we observe. Something in the early universe tipped the balance. What caused matter to win over antimatter remains one of the most important unanswered questions in cosmology. Even the nature of empty space remains mysterious. We often imagine empty space as truly empty, a void containing nothing at all. But quantum physics reveals that this is not the case. Even in a perfect vacuum, particles constantly flicker into and out of existence. Fields fluctuate. Energy seethes at the smallest scales. This vacuum energy may be connected to dark energy, but theoretical predictions overshoot observations by an enormous margin. Why the energy of empty space has the value it does is one of the greatest unsolved problems in physics. The emptiness between stars is anything but empty. Time may not flow the same way everywhere. According to Einstein's relativity, time is flexible. It slows down near massive objects and speeds up when gravity is weaker. Clocks tick differently depending on their motion and position in space-time. We have measured this effect with extraordinary precision. Atomic clocks on satellites run faster than those on Earth. Without correcting for time dilation, GPS systems would quickly fail. Yet this raises deeper questions. If time flows differently in different places, what is the true nature of now? Some physicists suggest that the present moment is not universal. Instead, all moments, past, present, and future, may coexist in a block universe where time is simply another dimension. In this view, the flow of time is an illusion created by consciousness moving through a fixed structure. Others argue that time genuinely passes and that physics has yet to fully capture this process. Whether time is fundamental or emergent remains unresolved. Free will may be an illusion or something entirely different. If the universe is governed by physical laws, do we truly make choices? In a deterministic universe, Every event follows inevitably from previous conditions. In a random universe, outcomes occur by chance. Where does that leave free will? Some philosophers argue that free will is compatible with determinism, that choices can still be meaningful even if they arise from prior causes. Others believe true free will requires indeterminism, a break from strict causality. Neuroscience adds to the puzzle. Experiments suggest that the brain may begin preparing decisions before we become consciously aware of them. And yet, subjective experience tells us we are choosing. Whether free will is an illusion, an emergent property, or something else entirely, remains one of the most debated questions at the intersection of science and philosophy. The human brain is the most complex object we know, and we still do not understand how it works. The brain contains roughly 86 billion neurons, each connected to thousands of others. Signals race through this vast network, giving rise to perception, thought, emotion, and memory. We have mapped many of its regions and identified their roles. We can watch activity unfold in real time. But understanding is not the same as explanation. We cannot yet explain how neural activity becomes experience. We do not fully understand how thoughts are formed, how creativity arises, or how consciousness integrates information. Even simple behaviors can be surprisingly difficult to trace through neural circuits. The brain created science, yet science has not yet fully explained the brain. The nature of intelligence itself remains unclear. Artificial intelligence systems can now recognize images, translate languages, and outperform humans in complex games. Yet do they understand what they are doing? What is intelligence exactly? Is it the ability to learn, to reason, to adapt, or to achieve goals? Is it consciousness or something separate? Human intelligence is flexible, creative, and deeply contextual. Machines excel at narrow tasks, but struggle with general understanding. Some researchers believe artificial general intelligence is inevitable. Others argue it may never fully replicate the richness of human cognition. We do not yet know whether intelligence is a single phenomenon or many different ones. Understanding intelligence, both natural and artificial, remains an open frontier. Meaning itself may not exist outside the human mind. Humans search for meaning in patterns, stories, and experiences. We ask why things happen and what they are for, but does the universe itself have meaning? From a scientific perspective, the universe follows laws without intention or purpose. Stars form, burn, and die without caring whether anyone watches. Some argue that meaning is something humans create, a narrative imposed on an indifferent cosmos. Others believe meaning emerges naturally from conscious beings and their relationships. There is no scientific experiment that can measure purpose. Whether meaning exists independently of minds or only within them remains a question each person must answer for themselves. The universe may be far stranger than anything we can imagine. Human intuition evolved to navigate a small world of solid objects and simple motions. It did not evolve to understand quantum fields, curved space-time, or cosmic scales. As science advances, reality grows increasingly unfamiliar. Particles behave like waves. Space bends. Time stretches. Cause and effect blur. Objects exist in multiple states until observed. These discoveries suggest that the universe does not operate according to common sense, and perhaps never did. Some physicists believe that reality at its deepest level may be completely abstract, described more accurately by information and mathematics than by physical objects. If this is true, the universe we experience may be a kind of projection, an emergent surface arising from deeper rules. Reality may be stranger than any story we could invent. We do not know whether the universe is fundamentally simple or irreducibly complex. Some scientists believe all of physics can ultimately be reduced to a few elegant principles. Others suspect reality is layered, with complexity arising at every level. So far, progress has revealed both simplicity and complexity intertwined. A single equation can describe a vast range of phenomena, yet solving that equation can be impossibly difficult. The universe may not have a final, simple explanation waiting at the bottom, or it may have one we have not yet recognized. Whether reality is built from a small set of fundamental rules or from an endless hierarchy of principles remains unknown. We may never find a final theory. Physicists often speak of a theory of everything, a framework that unifies all forces and explains all phenomena. But it is possible that such a theory does not exist. Nature may not be fully compressible into a single set of equations. There may always be new layers, new behaviors, and new mysteries emerging at different scales. Even if we discover fundamental laws, understanding how they give rise to the richness of the world may remain out of reach. Science may be an endless journey rather than a destination. This does not diminish its power. It highlights its beauty. Some truths may lie forever beyond observation. Science relies on observation, measurement, and testable predictions. But not everything may be accessible to these tools. Regions beyond the cosmic horizon, events before the Big Bang, and processes hidden behind black hole horizons may remain forever unobservable. We can model them. We can speculate, but we may never confirm them. This raises a profound question. Are there aspects of reality that exist but can never be known? If so, our picture of the universe will always be incomplete. And yet, science continues, not because it promises final answers, but because it deepens our understanding and expands our sense of wonder. Ignorance is not a failure. It is the beginning of curiosity. The greatest mystery may be that we can understand anything at all. Out of a universe governed by impersonal laws emerged minds capable of questioning those laws. Atoms arranged themselves into stars. Stars forged elements. Elements formed planets. And on at least one planet, matter became aware. We are the universe thinking about itself. How this happened, how complexity, consciousness, and curiosity arose, is still unexplained. And yet, here we are, asking questions in the darkness. The fact that the universe is understandable, even partially, may be its most astonishing feature. Perhaps the universe does not merely exist. Perhaps it unfolds. Some physicists suggest that reality is not a static structure, but a process. Not a finished object, but an ongoing becoming. In this view, the laws of physics themselves may evolve over time. The rules that governed the early universe may not be identical to the rules we observe today. Constants may drift. Symmetries may break. New behaviors may emerge. If true, then the universe is not just changing in content, but in character. This idea challenges one of the deepest assumptions of science, that the laws of nature are timeless. So far, no clear evidence confirms this, but the possibility remains open. Reality may be more fluid than we imagine. We often assume that the universe runs like a machine, predictable if we know all its parts. But complexity science paints a different picture. Simple rules can produce unpredictable outcomes. Small changes can cascade into enormous effects. Order and chaos coexist. Weather systems, ecosystems, and even the human brain follow this pattern. The universe itself may be a complex system, sensitive to its own history. If so, perfect prediction may be impossible, even in principle. Not because we lack information, but because the system itself generates novelty. The future may not be fully determined by the past. This challenges the classical idea of a clockwork cosmos. Some scientists believe the universe is fundamentally creative. New structures appear that were not explicitly encoded in the initial conditions. Galaxies form. Stars ignite. Chemistry blossoms. Life emerges. None of these outcomes were guaranteed. They arose from possibility interacting with chance. This does not mean the universe is random. It means it may be generative, a system that produces new forms as it evolves. If creativity is built into the fabric of reality, then the emergence of life and mind may not be accidents, but expressions of a deeper tendency. The universe may not only permit complexity, it may encourage it. We do not know why the universe allows complexity at all. Entropy drives systems toward disorder, and yet pockets of order continually arise. Energy flows create structure. Gradients give rise to patterns. Snowflakes form. Hurricanes organize. Cells maintain themselves against decay. Life is a local rebellion against entropy, fueled by energy from stars. But why do such processes exist? Why does the universe allow systems that temporarily resist decay and grow in complexity? This balance between order and disorder is delicate. Slightly different laws and complexity might never arise. The origin of complexity remains one of the deepest unsolved problems in science. Perhaps complexity is inevitable wherever energy flows, or perhaps it is rare and fragile. We do not yet know. Conscious observers may shape the universe they observe. In quantum mechanics, the role of the observer remains mysterious. Measurement seems to affect outcomes. Observation collapses possibilities into facts. Some interpretations suggest that observers are not passive witnesses, but participants. This idea has led to bold speculation. Could consciousness play a fundamental role in reality? Most physicists are cautious. No experiment shows that human awareness changes physical laws. And yet, the universe we describe is always filtered through observation. Every measurement is made from within the system. We cannot step outside reality to observe it objectively. This raises unsettling questions. Is the universe as it is, or as it appears to observers like us? The line between observer and observed may not be as sharp as we think. Human perception shapes the reality we experience. Our senses do not show us the world as it truly is. They show us a useful version of it. Color does not exist in objects. It exists in the brain. Sound is not carried through the air as music, but as vibrations interpreted by the mind. Even time and space, as we perceive them, are filtered through neural processes. The universe we experience is a construction, not a deception, but a translation. Science reveals that beneath this familiar layer lies a reality far removed from everyday experience. Atoms are mostly empty space. Solid objects are held together by invisible forces. The present moment is not universal, but relative. Reality is stranger than perception allows. And yet, perception is all we have. We live inside a model of the universe built by our brains. This raises a profound question. If our experience of reality is a simulation created by neural processes, how close is it to the truth? Evolution favors survival, not accuracy. Our senses evolved to help us navigate danger, find food, and connect with others, not to reveal the deepest nature of the cosmos. It is possible that large parts of reality are invisible to us, not because they are hidden, but because we lack the means to perceive them. Other creatures perceive the world very differently. Bees see ultraviolet patterns on flowers. Bats navigate by echolocation. Sharks sense electrical fields. Each species inhabits its own sensory universe. Humans may be similarly limited. There may be entire aspects of reality that lie beyond our cognitive reach. Some philosophers argue that intelligence itself has boundaries. Just as a dog cannot understand calculus, there may be truths that the human mind is simply not equipped to grasp. These truths may not be mystical or supernatural. They may simply be too complex, too abstract, or too alien for our neural architecture. If this is so, then some questions may never be answered, not because we lack technology, but because of who we are. This idea is humbling. It suggests that mystery is not a temporary condition, but a permanent feature of existence. And yet, humans continue to ask questions. Curiosity persists even in the face of limits. Perhaps the purpose of science is not to eliminate mystery, but to map its edges, to understand where knowledge ends and wonder begins. There is beauty in not knowing. Mystery invites imagination. It fuels creativity. It keeps the mind alive. A universe fully explained might be less inspiring than one that remains partially unknown. As night falls and the mind grows quiet, these questions soften. They do not demand answers. They simply exist. Like distant stars, shining whether we understand them or not. At night, questions feel different. In the quiet hours, the mind loosens its grip on certainty. Thoughts drift more slowly. Curiosity becomes gentle rather than urgent. Mysteries that felt overwhelming during the day soften into something almost comforting. We realize we do not need to solve everything to exist within it. The universe continues whether or not we understand it. Stars burn. Atoms vibrate. Time flows. Understanding is not a requirement for belonging. For most of human history, people lived beneath the night sky without answers. They did not know what stars were, or why seasons changed, or what dreams meant. Yet they told stories. They sang. They wondered. Wonder came before knowledge. Even now, despite centuries of science, wonder remains. Each explanation opens new questions. Each discovery reveals deeper unknowns. Science has not replaced mystery. It has refined it. The questions have grown larger, more subtle, more profound. We now ask not only how things work, but why anything exists at all. And still, silence answers back. There is something deeply human about resting within unanswered questions. To acknowledge that not knowing is not failure, but honesty. The universe does not owe us explanations. It simply is. And perhaps that is enough. As the body relaxes, thoughts begin to drift. Questions blur at the edges. Ideas fade like constellations slipping below the horizon. You do not need to hold them anymore. They will be there tomorrow. For now, you can let curiosity rest. Let the unknown remain unknown. Let mystery be gentle. Breathing slows. Muscles soften. The mind grows quiet. You are part of this universe, whether or not it is understood. And that is not frightening. It is peaceful. As the night deepens, the universe feels closer. Not smaller, not simpler, but more intimate. The vast distances between stars no longer feel overwhelming. Instead, they feel quiet, patient, timeless. The same laws that govern distant galaxies also shape your breathing, your heartbeat, the slow rhythm of your thoughts. Nothing about you is separate from the cosmos. The atoms in your body were forged in ancient stars. The iron in your blood was born in supernova explosions billions of years ago. You are made of the universe remembering itself. And yet, despite this deep connection, so much remains unknown. We do not know why the universe has the shape it does. We do not know whether time had a true beginning, or whether it stretches endlessly beyond our understanding. We do not know if reality has a final layer, or if every explanation reveals something deeper beneath it. Each answer feels like a doorway rather than a conclusion. Science often feels like progress toward clarity, but it is also a journey deeper into mystery. The more precisely we measure reality, the stranger it becomes. Particles lose their solidity. Space loses its emptiness. Time loses its simplicity. Even causality, the idea that causes always precede effects, begins to blur at the smallest scales. Reality resists being pinned down. It behaves less like a machine and more like a conversation, a dialogue between laws and chance, structure and freedom, order and surprise. Some physicists believe that uncertainty is not a flaw in our knowledge, but a feature of the universe itself, that unpredictability is fundamental. If this is true, then the future is not fully written. Possibility remains open. New patterns can emerge. New structures can form. The universe is not merely unfolding a predetermined script. It may be improvising. This idea can feel unsettling, but it can also feel comforting. It suggests that existence is not rigid, that novelty is allowed, that creativity is woven into reality itself. Life, then, is not an accident pressed into a hostile universe. It is one expression of the universe's capacity for complexity and change. And consciousness, your awareness right now, may be one of its rarest and most delicate expressions. The universe does not need to understand itself, but somehow, through you, it tries. As awareness drifts inward, the questions grow quieter. They no longer push. They no longer demand. They simply exist, like distant lights in the dark. You do not need to resolve them. The universe does not expect answers. It only continues. Every moment, reality renews itself. Particles appear and vanish. Fields fluctuate. Space stretches imperceptibly. Time moves forward, whether or not it is understood. And within this motion, life unfolds. Brief, fragile, remarkable. You are here for only a small span of cosmic time, a single breath in a universe billions of years old. And yet, during that breath, you can think, feel, imagine, and wonder. That alone is extraordinary. Most of the universe is silent. Cold clouds drift between stars. Empty space dominates everything. And still, on at least one small world, the universe became curious. It began asking questions about itself. Why is there something rather than nothing? Why do laws exist? Why does awareness arise from matter? These questions may never be answered fully, but asking them changes us. They stretch the mind beyond the immediate. They place personal worries into a larger frame. They remind us that we are part of something vast. In the quiet of night, this perspective can be calming. Problems shrink. Urgency fades. What remains is presence, the simple fact of being, breathing, existing, resting within mystery. You do not need certainty to find peace. You do not need conclusions to rest. The unknown can be a place of safety, not fear. A space where the mind can relax its grip, where thoughts drift like clouds, forming and dissolving without effort. As sleep approaches, curiosity softens into stillness. Questions dissolve into silence, and silence becomes rest. Sleep approaches not as an ending, but as a gentle turning inward. The mind loosens its hold on questions. Thoughts become softer, slower, less defined. The universe does not disappear as you drift toward rest. It continues quietly, patiently, just as it always has. Stars burn without sound. Galaxies turn without effort. Atoms vibrate in rhythms older than memory. Nothing needs your attention right now. Nothing needs to be solved. The great mysteries of existence are not urgent. They can wait. You are allowed to rest inside them. For a moment, there is no need to understand time. No need to define reality. No need to trace causes or imagine endings. There is only the present sensation of being here, breath entering, breath leaving, a slow, steady rhythm. Your body knows how to sleep. It has practiced this for your entire life. You do not need to guide it. You only need to allow it. As awareness fades, boundaries soften. The line between thought and feeling blurs. Images drift in and out, unanchored, unforced. This is the same mind that asks deep questions, now learning how to let go. Sleep is not ignorance. It is a different way of existing. A quiet state where the mind reorganizes itself, where memories settle, where emotions soften, where the brain tends to itself without effort. Even science does not fully understand sleep. We know it is essential. We know the body fails without it, but its deepest purpose remains unclear. And yet, it works, night after night. You surrender consciousness, and it returns to you in the morning. This small daily miracle requires no explanation. It only requires trust. As sleep deepens, the sense of self grows lighter. The borders that define you begin to soften. Thoughts slow until they no longer form sentences. They become impressions, sensations, gentle echoes. This fading is not loss. It is release. The mind does not disappear. It simply changes its shape. In sleep, the brain continues its quiet work. Neural pathways strengthen and weaken. Memories are sorted, trimmed, woven into new patterns. Emotions are processed without words. Problems that felt heavy may loosen their grip. Solutions may emerge later, unannounced, like gifts from the dark. This is not magic. It is the natural rhythm of a thinking organism. Consciousness recedes, but life continues beneath it. The heart keeps its steady pace. The lungs rise and fall. Cells repair themselves. Hormones shift. The body knows what to do. Across the planet, millions of other minds are doing the same, sleeping beneath different skies, in different rooms, in different cultures, all surrendering awareness to the same nightly tide. Sleep is one of the few experiences shared by all life with a nervous system, a universal pause, a quiet agreement between body and time. You are safe here. Nothing is required of you. The universe does not demand your attention. It does not need your understanding. It holds you regardless. As thoughts fade completely, there is no longer mystery or certainty. There is only rest. The deepest questions dissolve into silence, and silence becomes sleep. You have traveled far tonight, not through space, but through ideas, from the smallest particles to the largest questions, from the edges of the universe to the quiet center of your own awareness. Along the way, there were no final answers, only deeper understanding of how much remains unknown. And that is not a failure. It is a gift. To live in a universe that still holds mystery is to live in a universe that is alive with possibility. Every unanswered question is an open door. Every unknown is an invitation. Science does not end wonder. It refines it. It teaches us how vast reality is and how small our worries become when placed against it. As sleep settles fully, there is nothing left to do. No more thinking. No more searching. The questions you carried gently tonight do not need answers. They can rest with you. Like distant stars, they continue to shine whether you are awake or asleep. Your breathing slows. Your body grows heavy. The mind drifts into darkness, not empty, but calm. Tomorrow, curiosity will return. Questions will rise again. But for now, there is peace in not knowing. There is comfort in surrendering to rest. You are part of this universe, and tonight, you are allowed to sleep within it. Good night. May your dreams be quiet, vast, and filled with wonder.